there. Today we are going to talk about probability. Specifically, we're going to talk about simple probabilities, and then we're going to talk about what's called a compound probability, and then we're going to talk about what's called replacement. So calculating probabilities with and without replacement. So here's some definitions. We're going to start with talking about a sample space. But before we do, here's some definitions. So an outcome is a possible result of an experiment. For example, an experiment might be like flipping a coin, rolling a die, picking random names out of a hat. And an outcome would be one of those possible results. So if I'm flipping a coin, my outcomes would be like flipping a head and flipping and getting a tail. If I'm rolling a die, the outcomes would be rolling a 1, rolling a 2, a 3, a 4, a 5, or a 6. An event is a single outcome, or it could be a collection of outcomes. So for example, flipping a coin and getting a head is an event. That's an outcome, so therefore it's also an event. But also, if I roll a die, getting a 1 is an outcome, it's also an event. But I could also define the event to be rolling an odd number on a die. So anytime I roll an odd number on a die, that's an event. A sample space is the set of all possible outcomes. When I do an experiment, what are all the possible outcomes that I could see? All right, let's look at a couple quick examples. So if I toss 3 coins, it says how many possible outcomes are there? So tossing 3 coins, well, I know on each coin, I could get either a heads or a tail. So on like coin 1, it could be a head. On coin 2, it could be a head. And then on coin 3, it could also be a head. But I could also get a head on coin 1, a head on coin 2, and then a tail on coin 3. I could also get a head on coin 1, a tail on coin 2, and then a head on coin 3. Or I could get a head on coin 1, a tail on coin 2, and a tail on coin 3. Now you might notice I'm making an organized list. This is what we call an organized list. So first of all, I thought of all the possible outcomes that could happen if the head comes first. So if the first coin is a head, the second coin could either be like heads or tails, and then the third coin could either be heads or tails. So now I listed all the possible outcomes with coin 1 being a head. Now I'm going to think about, well, what if coin 1 was a tail? Then what could coin 2 and coin 3 be? It could be tail, head, head. It could be tail, head, tail. It could be tail, tail, head. Or it could be tail, tail, tail. So how many possible outcomes are there? There's 1, 2, 3, 4, 5, 6, 7, and then 8. Each of those is a possible outcome. So there's 8 possible outcomes. But I want to show you what's called the multiplication principle that could have gotten us that answer 8 a little bit quicker. I could think of, so what I just did was I listed out all the possible outcomes. But if I just wanted to know how many are there, I could think about, well, how many things am I doing? I'm flipping 3 coins, right? So I'm flipping like coin 1, coin 2, and then coin 3. So for each of those flips, how many possible outcomes do I have on each of those flips? Well, coin 1, there could be 2 possible outcomes. Coin 2, there could be 2 possible outcomes. Coin 3, there could be 2 possible outcomes. For each of them, they could either get heads or tails, so 2 possible outcomes. The multiplication principle says that if I multiply those things together, 2 times 2 is 4 times 2 is 8, that's going to give me the total number of possible outcomes, which kind of matches up with what we listed out, right? Okay, let's look at number 2. Let me erase this so we can see it. All right, so it says a spinner has 5 congruent spaces, numbered 1 through 5. You spin the spinner and toss a coin. How many possible outcomes are there? And this is the sample space again. So instead of listing them all out, I think about how many different things am I doing? I'm spinning the spinner and I'm tossing the coin, right? Well, how many possible outcomes are there when I spin the spinner? Well, the spinner has 5 congruent spaces numbered 1 through 5. So there's 5 possible outcomes. And when I flip a coin, what are the possible outcomes? Well, I could either get a heads or a tail. So there's 2 possible outcomes there. The multiplication principle says I can multiply them together to get 10 possible outcomes. If you had to list them, it would be like getting a 1 on the spinner and a head, getting a 2 on the spinner and a head, a 3 on the spinner and a head, a 4 on the spinner, a head, a 5 on the spinner, a head. Or it could be like a 1 and a tail, a 2 and a tail, a 3 and a tail, a 4 and a tail, and a 5 on the tail. Okay, that's sample space. Now let's look at probability. So the probability of an event is a measure of the likelihood or a chance that the event will occur. So what's the probability of rolling an odd number with 1 die? So to calculate this probability, you're going to think about how many possible outcomes are there. So when I roll a die, there are 6 possible outcomes. And then you're going to think about, okay, well, rolling an odd number. How many of those outcomes are odd? Well, when I roll a die, I could get a 1, 2, 3, 4, 5, or 6, right? So this is odd, and that's odd. So the probability of rolling an odd number is 3 out of 6, and I can reduce that to 1/2. You can actually list your probabilities as fractions. You could convert it to a decimal, or you could convert it to a percent. So any of those answers is fine. 0.5, 1/2, or 50%. Number 4, what's the probability that the month someone was born in begins with a J? Well, how many months of the year are there? There's 12 months of the year, right? And then think about those months. How many of them start with the letter J? Well, we have January, right? February, March, April, May, June, July, August, September, October, November, December, right? So there's 3 months of the year out of the 12 that begin with the letter J. So the probability that someone was born in the month that begins with the J is 3 out of 12, or in other words, 1/4. And again, you could list that as 1/4. You can convert it to 25% or 0.25. Okay, here's a couple more examples. So Dale conducted a survey of the students in his classes to observe the distribution of eye color. The table shows the results of his survey. Based on the survey, what's the probability that a student in Dale's class has blue or green eyes? So what we're going to do is we're going to say, well, how many total students are in the class? So you're going to have to add all these up. So I'll give you a minute to do that. So there should be 80 students. And then in question A, it says based on the survey. So based upon that survey that he did, what's the probability that a student in Dale's class has blue or green eyes? So there's 80 possible outcomes, or in other words, 80 possible students. We want to look at blue or green. So that could be these people, or it could be these people. One or the other. So when I see that word or, I add those 2 numbers together. So 12 plus 2 is 14. So there's a 14 out of 80 probability that a student in his class has blue or green eyes. And we can reduce this fraction, right? So this will reduce, a 2 goes into both 14 and 80, right? So this will reduce to 7 over 40. Okay, part B, based on the survey, what's the probability that a student in Dale's class does not have green or hazel eyes? So does not have green or hazel eyes. So again, we're out of the 80 because that's the total number of students, but we want not green. So I'm going to basically think about not these people or hazel eyes, so not those people. Well, what's left? that means they either have to have blue or brown eyes. So I'm looking at these people, the people that have blue or brown eyes, add them up, there's 70 of those people. So that probability is 7/8. Okay. Number 6, you spin a spinner that has 15 equal sized sections, numbered 1 through 15. Find the probability of the following. So what's the probability when you see that capital P here? This stands for probability. So what's the probability that the spinner lands on the number 15? Well, how many sections are there? There's 15 sections. And how many of those sections are numbered 15? So there's 15 sections numbered 1, 2, 3, 4, all the way up to 15. So there's only one section with the number 15 on it. So that should be 1 out of 15. How about the probability of an odd number? So there's 15 total sections, so that's always going to go on the bottom. And then think about your odd numbers. 1 through 15. So 1 is an odd number, 3, 5, 7, 9, 11, 13, 15. If you counted, which hopefully you did, there were 8 of those numbers. So the probability that the spinner lands on an odd number is 8 out of 15. Okay, how about the probability that the spinner does not land on 5? So again, there's 15 total sections. How many of them are not 5? Well, there's 1 5, right? So all the rest of them are not 5s. So there's 14 out of 15 sections that are not 5. So the probability is 14 out of 15. And then part D, less than 5. So again, there's 15 total sections. How many of them are less than 5? The sections less than 5 would be numbered 1, 2, 3, and 4. I would not include 5 because it says less than 5. If it was less than or equal to 5, I would include the 5. But in this case, there's 4 sections that are less than 5. 1, 2, 3, and 4. Right? Okay. So this one's a little bit more complicated. So let's take a look at this. 2 6-sided die are rolled and the sum is calculated. What are the possible outcomes? Well, if I roll 2 die and the sum is calculated, that means I add them together. The lowest number I could get is a 1 and a 1. That adds to a 2. Think about the highest number I could get. So I could get a 2, and the highest number I could get is a 12. So I could get any number, any whole number between 2 and 12. But here's the thing. These aren't going to all come out with equal probability because, for example, to get a sum of a 4. To get a sum of a 4, I could roll a 2 and a 2. Or I could roll a 1 and a 3 or a 3 and a 1. They all give me a sum of a 4. But to get a sum of a 1, of a 2, the only way I could get a sum of a 2 is to get a 1 and a 1. So I'm going to make a little table here. And whenever you see a problem like this, you should make a similar table. And I'm going to think about, well, what could happen on the first die and what could happen on the second die? On the first die, I could roll a 1, a 2, a 3, a 4, a 5, or a 6. And then on the second die, I could roll a 1, a 2, a 3, a 4, a 5, or a 6. And now I'm going to think about adding them together. So if I roll a 1 and a 1, a 1 and a 1, that would get me a sum of a 2. So you're going to see kind of if I were to draw like a little line, 1 and 1, give me a sum of a 2. So if I think about like a 2 and a 1, I would get a sum of a 3, right? If the first die is a 3 and the second die is a 1, that would be a sum of a 4. A 4 and a 1 would be a sum of a 5. A 5 and a 1 would be a 6. A 6 and a 1 would be a 7. I'm adding these all together, right? Because we said that sum means add them together. On the other hand, if I rolled a 1 on the first die and then a 2 on the second die, that would be a sum of a 3. A 2 on the first die and a 2 on the second die would be a sum of a 4. And hopefully you can kind of see the pattern now. I'm adding up the two numbers on the top column and the side row there. So fill in your table. And I'll fill in mine. And you'll see it definitely follows like a pattern. And ultimately, like we said, the smallest number you could get is a 2, and the biggest number you could get is a 12. And we can get any whole number in between. So now think about how many possible outcomes are there. There's actually going to be 36 possible outcomes. Or in other words, the sample space has 36 outcomes. Now, I could have calculated this using my multiplication principle. Remember? How many things am I doing? I'm rolling die 1, and then I'm rolling die 2. How many outcomes are there on die 1? How many outcomes are there on die 2? What's 6 times 6? 36, right? So 36 possible outcomes. So find the following probabilities. Find the probability that the sum is greater than 4. So out of 36 possible outcomes, how many of them are greater than 4? So greater than 4 would be 5, 6, 7, 8, 9, 10, 11, or 12. So basically, you have to count up how many numbers are here. And it might actually be easier to count up how many numbers are 4 or less and take that away from 36. I can see that 2, 3s, and 4s, there's 1, 2, 3, 4, 5, 6 of them. So 30 minus 6 is, 36 minus 6 is 30. So if I were to count up how many numbers I have there circled in red, it would be 30 out of 36. And I could reduce that to 5, 6. All right, what's the probability that the sum is 6 or 11? So now I'm going to go through and count up, well, I'll circle these in black because this is going to get kind of confusing with all the circles here. 6 or 11. That would be all those things that I circled in black. How many numbers are in black? 1, 2, 3, 4, 5, 6, 7. So it would be 7 out of 36. And that actually can't be reduced. How about the sum is neither 5 nor 9? So we did one similar to this in the last question. When it's something like neither, it means we don't want those numbers. So we don't want a 5, so I'm going to X out. And I don't want a 9. So I used green here. So basically, you want to count up how many numbers did I not X out in green. It might be easier to count how many numbers did I did X out in green. 1, 2, 3, 4, 5, 6, 7, 8, and subtract from 36. So 36 minus 8 is 28. And we can reduce this. I know that 2 go, oh no, you know what, 4 goes into both of these, right? So this is going to be 28 divided by 4 is 7, 36 divided by 4 is 9. So 7 out of 9. Okay, part D. The sum is greater than 7 and less than 11. So greater than 7 and less than 11. Well, what could that mean? What numbers are greater than 7? 8, 9, 10, and less than 11. I have to stop there, right? I want to include the 11. So I need to think about, well, how many of these are how many 8s, 9s, or 10s are there? So I'm going to count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 out of 36. And if I reduce that, 12 goes into both 12 and 36, right? So 1/3. Okay, the sum is even or odd. All right, well, let's think about this. Even or odd, well, 2, 4, 6, 8, 10, 12, those are the evens, right? The odds are 3, 5, 7, 9, 11. That's every number up there. So out of all the 36 numbers, all 36 of them are either even or odd. In other words, there's a 100% chance when I pick a number or roll two die and add them together that the sum is either going to be even or odd. Okay. So that is basic probability. Now we want to talk about what's called a compound event. A compound event is when there's more than one event happening at the same time. And to find the probability of a compound event, you're going to actually take the individual probabilities and then multiply them together. So when you see the word and or something that means and, like both, that means and, that's when you think compound event and then you think multiply. So quick recap, when we saw or, we added together. When we see and, we're going to multiply together. Let's look at some examples. A spinner has 5 congruent spaces numbered 1 through 5. You spin the spinner and toss a coin. What's the probability of getting a 3 followed by a head? So basically, we want the probability of spinning a 3 and then flipping a coin and getting a heads. So when I see the probability of both or the probability of and, this and that, remember we calculate the individual probabilities and then we multiply them. So what's the probability of spinning a 3 on this spinner? So there's 5 possible outcomes. They're all congruent. So 5 goes on the bottom. And how many of them are numbered 3? Well, there's one of them that's numbered 3, right? And then what's the probability of flipping a coin and getting a heads? Well, there's 2 possible outcomes on a coin, heads or tails, and one of them are heads, right? So to find this probability, I would multiply 1 over 5 times 1 over 2. So 1 times 1 on the numerators and 5 times 2 on the denominators, it would be 1 out of 10. And if you think about this, we actually thought about this when we did our sample space. Let me go all the way back. Oh, I went too far. So this second example here, when we did sample space, we said there's 10 possible outcomes. We didn't list them out, but if I listed them out, oops. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 10 possible outcomes, like we said. And this question was, what's the probability of getting a 3 followed by a heads? So look, a 3 and a heads. There's one of them that's a 3 and a head out of 10 possible outcomes. That's why that probability is 1/10. Okay, number 9, you roll a die twice. What's the probability you roll 4 and then you roll an odd number? So in other words, we see the word and, so we think about each probability and then we multiply. We want the probability of rolling a 4 times the probability of rolling an odd number. Okay, so when I roll a die, there's 6 possible outcomes. How many of them are 4? Well, there's only one 4, right? It's either 1, 2, 3, 4, 5, or 6. So there's 1 out of 6 chance of rolling a 4. But then if I roll another die, or if I roll even the same die again, there's 6 possible outcomes. What's the probability of getting an odd? Well, it would be a 1, a 3, or a 5. So there would be 3 possible outcomes that are odd. So I would multiply these things together. 1 times 3 is 3. 6 times 6 is 36. And then I can reduce this. 3 goes into both. And so my probability would be 1 out of 12. Okay, so now let's talk about compound events, and let's talk about what it means to replace or use without replacement. So you'll see what I mean. Let's get into this. Ready? A drawer contains 12 white socks and 8 black socks. So before I do anything, let's think about this. There's 20 total socks in the drawer, right? You randomly choose one sock, and then you replace it. And then you randomly choose another sock. So this is like I'm doing two things, right? What's the probability that both socks are white? So kind of like what we said before, this is a compound event. I want the probability that the first sock is white, and then I want the probability that the second sock is white. But here's the thing. It says, and then you choose the sock, and then you replace it, okay? So let's think about it. The probability of the first sock being white, well, there's 20 socks in the drawer. How many of them are white? 12 of them are white, right? So the probability that the first one's white is 12 out of 20. But I take that sock out, but then I put it back in. They tell me then I replace it. So what's the probability that the second sock is white? There's still 12 white and 20 total socks in the drawer. So it's still 12 out of 20. I got to multiply these. And it actually might be easier for me to reduce these fractions first before I multiply. 4 goes into 12 and 20. And so I'm going to actually make this 3 over 5 times 3 over 5, which is 9 over 25. And if you had just multiplied and then reduced, you would have still gotten the same answer. So that probability is 9 out of 25. But look at number 11. From the same drawer, what's the probability you chose a white sock and then you leave it out? So in other words, this is what we call without replacement. I take the first thing out and I don't put it back in. And then you choose another white sock. So I'm really thinking about the same thing. I want the probability that the first sock is white and sorry. Okay. And the second sock being white. But now this is without replacement. Let's see how that looks different. Okay. So the probability that the first sock is white. There's 20 socks in the drawer. 12 of them are white. So 12 out of 20. But here's the thing. I didn't put that sock back in my drawer. I left it out, or I put it on my foot. In other words, without replacement. So now I don't have 20 total socks in the drawer. Now I only have 19 socks in the drawer. And the reason I only have 19 socks in the drawer is because I no longer have 12 white socks. I have 11 white, and I still have 8 black, right? Because the first one I took out was white. So now what's the probability that the second sock is white? Well, now there's only 19 total socks, and only 11 of them are white. So without replacement changes the probability of the second event. So now I got to multiply these things together. Again, I'm just going to real quick reduce 12 over 20 gives me 3 over 5 times 11 over 19. And this will be what? 33 over 95, I think, right? So 33 over 95, that's my probability there. And if you type that into the calculator to give yourself a decimal, 9 over 25 and 33 over 95, the answer to 10 and 11, they're going to be close decimals, but they're not going to be the same. Okay, so let's think, again, more about like replacement versus not replacement. You have a closet with the following shirts: 3 blue, 4 yellow, 2 white. So I have a total of 7, 8, 9 shirts. So 9 total shirts. Okay, what's the probability of getting a blue shirt, then a yellow shirt with replacement? So I need the probability of a blue times the probability of a yellow but with replacement. So the probability of a blue, well, there's 3 blue out of 9, right? With replacement, that means I'm putting it back, so there's still 9 shirts. Now what's the probability of a yellow? There's 4 yellow, right? So I'm going to reduce this first just to make it easier. To multiply, my answer should be 4 out of 27. Now, same thing. What's the probability of getting a blue and then a yellow, but now without replacement? So the probability of getting a blue shirt, the first shirt, is still 3 out of 9. But without replacement means that I now took one of these blue shirts out. So I now only have 2 blue shirts, and that means I have 8 total shirts. So what's the probability of getting a yellow? Now the probability of getting yellow, there's 4 yellow, but there's only 8 total. So it's 4 out of 8. All right, to multiply these, again, I'm going to reduce. 3 out of 9 reduces to 1/3. 4 out of 8 reduces to 1/2. So this probability is 1 out of 6. All right, the probability of getting a yellow then a yellow without replacing. So I'm going to kind of reset here. We're going to reset. Go back to 9 total shirts. So the probability of a yellow times the probability of a yellow without replacement. So the probability of the first shirt being yellow is 4 out of 9. But without replacement, again, that means I take out that yellow shirt. So now I only have 3 left, which means I have like 3 plus 3 plus 2, which is only 8 total shirts. Now, what's the probability my next one's yellow? Well, how many yellow shirts do I have? Only 3 now, right? So 3 out of how many total? Now my total is only 8. Okay? So now I'm going to multiply these together. And then I can reduce this fraction. And that'll reduce to 1/6. Okay. Part D, blue then white with replacement. So the probability of blue times the probability of white, but with replacement. And again, let me kind of reset my drawer here, or my closet. 9 total. Okay, with replacement. So the probability of a blue is 3 out of 9. With replacement means I'm putting that one back. So everything kind of stays the same. Now the probability of a white is 2 out of 9, right? So I'm going to reduce the 3 out of 9 to 1/3. And I would get 2 out of 27. All right. Thanks for watching. There is your lesson with probability.